Large Language Models, or LLMs, are a revolutionary type of artificial intelligence designed to understand, process, and generate human language on a massive scale. If you've ever used tools like ChatGPT, Gemini, or Microsoft Copilot, you've experienced an LLM in action. They're not just advanced chatbots. LLMs analyze context, infer intent, and generate surprisingly thoughtful, persuasive, or even creative responses. Their capabilities extend far beyond simple keyword matching, enabling tasks from summarizing documents to writing poetry or generating code. At their core, LLMs operate on a fundamental principle: prediction. Given a sequence of text, the model's primary goal is to predict the most likely next word or token in that sequence. This seemingly simple task, repeated billions of times across vast datasets, is what allows them to generate coherent, human-like language. The large language models refers to two key aspects: the immense amount of data they are trained on, and the sheer number of parameters within their neural networks. These models are pre-trained on trillions of words from diverse sources like books, articles, websites, and code. Some of the most powerful LLMs have hundreds of billions, even trillions, of parameters, allowing them to learn incredibly complex patterns and relationships within language. The foundational architecture underpinning most modern LLMs is the transformer model, first introduced in 2017. Unlike older neural networks that processed words sequentially, the transformer architecture excels at processing entire sequences of text in parallel. This parallel processing significantly enhances their efficiency and scalability. A critical first step in how LLMs process information is tokenization. Raw text, which machines cannot directly understand, is broken down into smaller units called tokens. Tokens can be whole words, subwords, characters, or even punctuation marks, depending on the tokenizer's design. Each token is then assigned a unique numerical ID, transforming the text into a format the model can process mathematically. Once tokenized, these numerical representations are converted into embeddings. An embedding layer creates vector embeddings, which are mathematical representations of the words that capture their semantic and syntactic meaning. This allows the model to contextually understand words and their relationships, even considering their position within a sentence through positional encoding. The heart of the transformer architecture lies in its attention mechanism, specifically self-attention. This mechanism enables the model to dynamically weigh the importance of different words in a sentence relative to each other, considering their context. For example, in the sentence "the cat sat on the mat because it was warm," the attention mechanism helps the model understand that it refers to the mat, and not the cat. The transformer model typically consists of multiple layers of encoder and decoder blocks. Encoder layers process the input sequence, creating contextualized representations, while decoder layers generate the output sequence, often autoregressively, meaning they predict one token at a time. Many LLMs like GPT primarily use decoder-only architectures for text generation. Training an LLM involves a multi-stage process. The initial stage is pre-training, where the model learns general language patterns, grammar, facts, and reasoning by being exposed to massive, unlabeled text datasets. During this phase, the model iteratively adjusts its parameters to predict the next token in a sequence, gradually improving its ability to generate coherent language. After pre-training, LLMs are often fine-tuned on smaller, task-specific datasets. This supervised learning process involves training the model on labeled examples, typically input-response pairs, to adapt its behavior for specific applications like sentiment analysis, question answering, or customer service chatbots. Fine-tuning helps the model specialize while retaining its general language understanding. Another crucial step is alignment, often achieved through reinforcement learning from human feedback. While pre-training teaches the model the structure of language, alignment teaches it how to respond in a helpful, honest, and harmless way, reducing hallucinations or the generation of incorrect or nonsensical information. Humans compare model outputs and express preferences, and a reward model is trained on these preferences to further optimize the LLM. The applications of LLMs are vast and continue to expand. They are transforming customer service through intelligent chatbots and virtual assistants. LLMs excel at content creation, copywriting, and generating various forms of text. They are also highly proficient in language translation, code generation, summarization, and sentiment analysis. Despite their impressive capabilities, LLMs do have limitations. They can struggle with complex multi-step logical reasoning and may produce incorrect or nonsensical responses, a phenomenon known as hallucination. LLMs are also only as good as their training data, meaning they can inherit and amplify biases present in that data and may provide outdated information if not frequently retrained or updated. Nevertheless, large language models represent a significant leap forward in artificial intelligence, making technology more intuitive and powerful than ever before. Their ability to understand and generate human language is revolutionizing how we interact with information and shaping the future of many industries.